So I'm going to go through the questions that, as a class, you found the hardest from that multiple choice questions on light. First one was number 8. Now in this one, the first thing to spot is that the ray is coming in along here and then going along the surface from the glass to the air. Now you've got to remember this is a special case, and this is when this angle here, the angle of incidence, is equal to the critical angle. So in this case, the critical angle is going to be 90 minus 50, given that this area here is a right angle, so 90 minus 50 to get this angle here. So that will be 40 degrees. So we know the critical angle is 40. To find the refractive index, then you need to remember this equation, which is one of the ones you need to learn. N equals 1 over sine c. Nice and easy, this one, because you just put the numbers into your calculator. So I just type in 1 divided by sine 40. That gives me 1.555. Notice that these are all round to 3 sig figs, so we round here, so that's going to become 1.56. So our answer is D. Let's have a look at this one now. Yes, quite a few asked about this one. This is a really good question here. We've got radiation from the sun coming in. So the sun emits a broad range of waves from the electromagnetic spectrum. It says the prism does not absorb any of the radiation, so that we know that it's all going to get through. 4 thermometers are placed at each of these positions A, B, C, and D. In which position do we get the greatest rise in temperature? Now, what we've got to do is think about what is related to temperature, what part of the electromagnetic spectrum. And if you remember, it's to do with infrared. The infrared part is related to heat. The hotter something is, the more infrared it emits. So where are we going to get the greatest rise? Well, that's going to be where there's the most infrared radiation. Now, if we look here, this is the red end of the visible spectrum. Well, just beyond that, if you remember your order, is infrared. If we keep going up, we'll have radio waves up here somewhere, microwaves, and so on. There's infrared there. Just below that, we've got violet, and hopefully you remember that just beyond violet, well, the clues in the name, ultraviolet and infrared, so you know which part they come near. Ultraviolet comes just beyond violet, and we keep going down towards gamma down here. So where's going to be the hottest? Well, it's where the infrared is located, so it's just beyond the red bit, so the answer is A. So I think a lot of you didn't get that one because you didn't realise that temperature or hotness of something is related to how much infrared radiation emitted. The hotter something is, the more infrared it gives off. Likewise, the more infrared you receive, the hotter you will feel. Which statement about a converging lens is not correct? So a lot of you went for A on this one. A ray parallel to the principal axis of the lens is refracted through the principal focus. So just remember, we've got our lens here. We've got our principal axis. This is the principal axis here. Now, if a ray comes parallel to the principal axis, that means here, here, anything that's parallel to this line here, will go through the principal focus. Well, yes, remember, any ray that comes parallel goes through the principal focus, and if it's on the principal focus, it just continues straight and still goes through the focal point. So that is correct. All rays of light refracted by lens pass through the principal focus. Well, that's not true. If I send a ray in like that, well, you know, the classic example going through the middle of the lens, that doesn't go through the principal focus. So that is not correct. So we know the answer is B. Just to check the other two, the distance between the centre of the lens and principal focus is the focal length. If you remember that, that is correct, because that's the definition of the focal length. It's the distance from the centre of the lens to the focal point. And the principal focus of the lens is a point on the principal axis. Well, yes, that's where it's always located, as we know, so that is correct. Going down here, this is about water waves, demonstrating refraction by making them pass into water of different depths. Why does the water wave change direction as it passes into the shallow water? Well, remember, the change in direction, the refraction, is all to do with changes in speed. Okay, and what you must remember is frequency is constant during refraction. So as we said, we know frequency is constant. That's what I was just mentioning. Sorry, I had to cut the video there just to edit away some stuff. Now, as we know, frequency is constant. These two are ruled out, as I've shown there. And hopefully you remember that when we're in shallower water, water waves slow down. So it's because the speed of wave decreases. And what you can actually do is think about, well, the normal, which would be here. And you can see that this ray should be going like that, but it's actually bent to here. So it's bent towards normal. That only happens when the waves slow down. Only a couple more to go. This one here. Teacher demonstrates the dispersion of white light using a triangular glass prism. Which diagram shows how this dispersion happens? So the first thing to spot the difference between the ones on the left and the right is you notice, I'm going to use my cool coloured pen here because it's to do with dispersion. Dispersion, remember, is where white light splits up into the visible spectrum. So you get red, orange, yellow, green, blue, indigo and violet. And if you see here, there is no spreading out happening inside the lens. Well, that is wrong. Okay, dispersion starts from the moment refraction starts, which is at the first glass face. The light slows down, so we get spreading. Remember, this is because red, and blue, or violet, bend by different amounts because they have different refractive indexes. Different N in glass. And that's why we get dispersion, is because they bend by different amounts, because they have different refractive indexes. So dispersion happens as soon as it enters. The next thing to do is perhaps draw the normal on to these surfaces. So in the exam, you'd get your protractor or your ruler, make sure it's right angles to the surface. So there's the normal for that one. And let's have a look at this one. Normal would be about there. And you're starting to spot something. That this one is actually coming in on, normal would be about there, it's actually coming in on the normal. Remember, when light comes in on the normal, so the angle of incidence, is actually 0, because it's coming in on the normal. Remember, you measure the angle from the normal. So you get no refraction. Remember, it just continues in a straight line like that. So that means B would be correct in this situation.